Welcome to the 30th lecture of graph theory. In the last class, we were going through the proof of Chvatal's theorem about a sufficient condition for the existence of Hamiltonian cycles. The theorem is stated like this: if G is a graph with n vertices and degree sequence d1 less than equal to d2 less than equal to dn, then it's called Hamiltonian if every sequence which is pointwise greater than or equal to this given sequence is corresponds to graphs which are Hamiltonian. That means, if a graph has this as its degree sequence, then it should be a Hamiltonian graph. So, an integer sequence a1, a2, an such that 0 less than equal to a1 less than equal to a2 less than equal to an strictly less than n is Hamiltonian if and only if the following holds. This is the condition: for every I strictly less than n by 2, if ai, the number in the ith position, is less than equal to I, then the corresponding number an minus I, that means if you count from the other end, the I plus 1th number has to be greater than equal to n minus I. If this condition is met, then it will be Hamiltonian. That sequence will be Hamiltonian. That means, not only this, the graphs with this sequence, and all graphs with the sequences which is pointwise greater than equal to this will be Hamiltonian. And so, we have shown why, for instance, if this condition is satisfied, then all sequences which is pointwise greater than equal to this sequence corresponds to graphs which are Hamiltonian. Now, we will look at the other side, namely think about the graphs. So, a sequence which does not satisfy this condition. That means, suppose for some I, you are given a sequence, suppose some I, for some I less than n by 2, it so happens that ai is in fact less than equal to I. So, maybe you can some h, we can just change the notation to h is less than equal to n, but the corresponding inequality is not correct. A n minus h is not greater, that is also less than equal to n minus h. It is not greater than or equal to n minus h, right. So, then so see, let us look at it, greater than equal to n minus h. Then suppose this is, if we want it to be greater than equal to n minus h. So, suppose it so happens that it is not greater than equal to n minus h, it is strictly less than n minus h, right. So, now we will construct a graph which is has a degree sequence which is pointwise greater than this, but does not have a Hamiltonian cycle, right. So, the how do I construct, because then we want to say that if this any sequence which does not satisfy this condition, the Chvatal condition, will be such that there exists at least one graph which has a pointwise greater degree sequence compared to the given sequence, and which is not Hamiltonian. That means, it is an if and only if statement for it characterizes the Hamiltonian sequences. Not that if it satisfies, it is always Hamiltonian. If it does not satisfy, it is sometimes Hamiltonian, sometimes not Hamiltonian. It is not that. If it does not satisfy somewhere, then you can always find some graph which has a degree sequence which is pointwise greater than equal to this, but does not have a Hamiltonian cycle. So, how do we see this thing? So, this is the construction. So, let us construct a graph like this. There are take H vertices. Now, you take H vertices here. This is 1, 2, 3 H, right. Now, here we will take the remaining n minus h vertices, but here this will correspond to 2h. The h vertices are special and the remaining vertices are different. Now, the point is to construct a graph with a degree sequence equal to, see, initial what we are going to do is to connect all these vertices to the corresponding h vertices here, right. That means the degree of each of these vertices will be h. So, that the degree sequence will start with h, 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 etc. How many times? So, h times, right. So, then so that our h number will be h, that is a h will be less than equal to h. Now, these vertices are universal vertices, right, because they will connect to everything, because we will make it a complete graph here, right. So, but on the other hand, here these vertices up to, this is nth vertex, this is n minus 1th vertex, this is n minus h plus 1th vertex. So, n minus h plus 1th vertex onwards, the position onwards, we will have n minus 1 degree, n minus 1, n minus 1 degree, and then the remaining vertices will have degree. These are the remaining vertices. They will have degree n minus 1 minus h, that means n minus h minus 1. So, the degree sequence will be h. So, I am writing the position numbers here, I have 1, 2, 3, 4 up to h. So, h, h, h up to here, this is h, and then h plus 1, h plus 2 till n minus h minus n minus h, we will have the numbers n minus h minus 1, n minus h minus 1 up to here n minus h minus 1, and from here onwards n minus h plus 1 onwards to n, we will have n minus 1, n minus 1, n minus 1. The point is that if you look at the hth number ah, that is equal to h, this is less than equal to h. So, the ah is less than equal to h. Then we would, Chvatel's condition says we should have a n minus h should be greater than or equal to h, right. N minus h should be greater than equal to n minus h. But if you look at the n minus h, the number, this is only n minus h. So, n minus h minus this is equal to n minus h minus 1. So, this is not true, this is violated. So, the condition is violated. So, that is the way the graph is constructed. So, you may ask, so how is it true that, so my sequence was something else initially, a1, a2 up to ah. I only knew that ah is less than equal to h, right, and here these numbers were anything which is maybe greater than or equal to this thing a n. This was the initial sequence. How can I take this sequence, right, instead of this sequence? That is because this sequence is pointwise greater than this, because here this number was anyway less than equal to h. So, all these numbers were less than equal to h. We just increased the values here to h. So, and also we knew that here the h minus 1th number was strictly less than n minus 1. The maximum possible was n minus h minus 1, and all these numbers can be at most that much 1. So, we just increased all the possible numbers here, all the numbers here. It is possible that they were already n minus h minus 1, or it is possible that they were strictly less than. If they were strictly less than, then we increase them to this number. It's not possible that their values were actually greater, a n minus n plus 1 to h plus 1 to a n minus h. Any of these numbers cannot be strictly greater than n minus h minus 1 initially, because in that case how can this number a n minus h be strictly greater than n minus h, right, because all these numbers are supposed to be smaller than or equal to this number. And the later numbers we made it as big as possible, namely n minus 1. So, therefore, whichever is this initial sequence a1, a2, ah, an h plus 1 to an, we have just increased the corresponding values. Every ai has only got increased. Therefore, this sequence is a pointwise greater degree sequence, greater than or equal to the original given sequence, right. So, therefore, we just have to show that this sequence corresponds to a non-Hamiltonian graph. Some graph exists with this sequence, but not Hamiltonian. That is enough to show that for any given this sequence which violates the condition will lead to a pointwise greater than equal to a sequence which is pointwise greater than or equal to this, having degree sequence which corresponds to a graph which is not Hamiltonian. So, which is that graph? The graph is this we have constructed, namely, see this, these are all h, the smallest values are coming from these vertices. So, I will mark it as red vertices, see. So, the next, so because these are all degree h, right, these all degree h, because here there is no, it is an independent set, it is connected to all the last h vertices. And on the other hand, these vertices are the last h vertices, namely nth, n minus 1th up to n minus h plus 1th vertex, and they all have degree n minus 1. These are the vertices which come in between with the degree n minus h minus 1, because they are connecting to all vertices in this part except these h vertices. Therefore, n minus 1 minus h is their degree, right. Now, we claim that this graph cannot have a Hamiltonian cycle. Suppose it has a Hamiltonian cycle, then what is wrong with it? Suppose, so if there is Hamiltonian cycle, you can identify these red vertices in the Hamiltonian cycle. So, in the but these vertices, red vertices are non-adjacent vertices, they are independent set, they are an independent set. So, in a Hamiltonian cycle, for instance, if you locate them on a Hamiltonian cycle, so it may come like this, a red vertex, a red vertex, a red vertex, a red vertex, a red vertex. How many neighbors they should have in the Hamiltonian cycle? So, here if I count this neighbor 1, right. So, and this neighbor, so this neighbor, it is possible that every consecutive red k may share this neighbor. So, like that, and finally here, unless this number was strictly equal to n by 2, then we can clearly say that the number of neighbors of this set, this red set, that means the number of neighbors such that it is adjacent, so the number of vertices such that they are adjacent to at least one red vertex is at least one more than the number of vertices. We know that this number of red vertices is h, that is strictly less than n by 2. Therefore, these last two vertices cannot be the same. So, therefore, though even if we say that these are all shared neighbors, these two cannot be shared neighbors. We should have one more neighbor than h for this set in the Hamiltonian sequence. But on the other hand, if you look here, this has only exactly h neighbors. We don't have enough neighbors. If there is a Hamiltonian path, it's not possible to have just h neighbors, because there are more vertices here, right. So, in other words, if you want to see it in a different way, the Hamiltonian path will go here, then it has to come back here, then again it has to go here, it has to come back here. So, every time it goes here and come back, then you have to account for one more vertex, and finally, because the cycle has to close, right, it has to come out of it, right. So, therefore, it need to, once it enters through one vertex and once it come out through one vertex. So, therefore, there should be one more vertex to which in the neighborhood of h, exactly h neighbors are not enough. So, we see that this is not a Hamiltonian graph. So, therefore, we have shown that if the Chvatal condition is violated, then whichever is the sequence, if it is violated, even in some AI, some AH less than equal to h, the corresponding an minus h is not greater than equal to n minus h. If it happens to be less than equal to n minus h minus 1, then we know that there is a graph which is whose Hamiltonian whose degree sequence is pointwise greater than or equal to this sequence and is not Hamiltonian. So, therefore, Chvatal's condition characterizes the Hamiltonian sequences, right. So, that is what the theorem says. Now, now our aim is to look at some of the related theorems in Hamiltonian regarding Hamiltonian circuit. In this class, we will spend some time to understand some of the related results in regarding Hamiltonian cycles, and from the next class onwards, we will start on a different topic. That is our aim. So, here is another concept. So, this is called the toughness of a graph. So, suppose you remove some s vertices from the graph. Remove s vertices from G, then and then count the number of components in G minus s. If it so happens that the number of components in G minus s is less than equal to cardinality of s, then we will say that G is tough. G is a tough graph. So, G is one tough is another, because you can generalize this concept further, just one tough. So, for example, if you say an example, so suppose if you take a cycle, right, and you try to remove two vertices here, right. So, maybe you can remove these two vertices. Then how many components results? Only two components results. The number of components which resulted is only 2. Now, you can try removing more vertices, maybe. Yeah, so suppose it's a big cycle, and now let us try to remove some more vertices. See how many vertices are removed. Here we try to remove 4 vertices. The number of components which results is 1, 2, 3, 4. 4 vertices removed and 4 components resulted. So, in some cases this may not be true. For instance, you take a path. So, in a path, let us try to remove some vertices. Here 1, 2 vertices, you get see 1, 2. The number of components is more than the number of vertices removed. 1, 2, 3, right? 3 components resulted from that. So, it is not tough. So, the toughness essentially means that if whichever number of vertices if you remove, then in the remaining graph the number of components is less than equal to the number of vertices that you have removed, right. And see, of course, this concept can be generalized. So, see here you show a graph which is not tough, which is, and we also show a graph which is tough, and you see the way to generalize it is to give, say, you can give arbitrary values of t. For instance, let t greater than 0 be a real number. Then you can probably ask, suppose I remove S, the set of S, S be the set of vertices I remove from the graph, any set which you remove, then can I guarantee that the number of components in G minus S is less than equal to cardinality of S by T? For any S it should happen, right? Whichever collection of S vertices if you remove, the number of components in G minus S has to be less than equal to S by T. Then we will say that G is T tough. Put T equal to 1, we get the original definition of tough. So, toughness means 1 toughness, right. So, why is toughness interesting in the case of in the context of Hamiltonian circuits? So, the toughness is interesting because you see that if a graph is Hamiltonian, it has to be tough, it has to be at least 1 tough. Why is it so? It is because you take a set S vertex. Suppose you have a Hamiltonian cycle in the graph. Now, you take any arbitrary set S of vertices, let us say this is S. Now, it so happens that the number of components that resulted is more than S. So, that means the number of components we got in the resulting graph, when you remove this S, right, then the number of components 1, 2, 3, 4, 5, how many of them? This is greater than cardinality of S. So, it is not a tough graph, but is it possible that there is a Hamiltonian cycle in it? But if it so happens that there is a Hamiltonian cycle, so it should be that, so we should have a portion of the Hamiltonian cycle here. So, whenever the Hamiltonian cycle goes out of this, it should enter here, right. Similarly, for each of this thing, so at least one vertex, through one vertex it should go in, and then through one vertex it should come out. Maybe the same vertex can be used to go out of this thing. So, we should account at least one vertex for entering each component. So, if you are thinking that you are starting from a vertex in S, you can enter through that vertex to one of the component, finish off that component and come back, and then you can enter another component from that. Every time to enter a component you need one new vertex, right, and finally you can come back to the original vertex, it is okay. So, therefore, we need at least as many vertices as there are components. For instance, if there are more components than there are number of vertices, you will not even be able to enter a component without repeating a vertex, without revisiting a vertex of S. So, that is it is an obvious thing. In fact, the number of vertices in S has to be at least as much as the number of components, otherwise you cannot have a Hamiltonian cycle, right. It is very clear. So, therefore, toughness is a necessary condition for Hamiltonicity, but on the other hand toughness need not be a sufficient condition for Hamiltonicity. Is it possible for you to draw a graph which is Hamiltonian, but which is not tough, but still Hamiltonian? Is it possible to draw? So, that is an interesting exercise. You can try to draw some graph which is Hamiltonian, which is not tough. So, I will leave it to you to try that. So, but it is not very difficult to find out some graphs where Hamiltonicity is available even without toughness. So, the point here is that toughness is not enough to ensure the Hamiltonicity, but toughness is indeed a necessary condition. Sufficiency is not there, so it is not sufficient. So, therefore, what we can see is that, but on the other hand, if you increase the toughness of a graph a little bit, if you increase the toughness of a graph a little bit, is it possible that the graph may become Hamiltonian? For instance, look at this conjecture. A graph is called, suppose the graph is some t tough for a greater value, right. So, this is a toughness conjecture by Chvatal. It says there exists an integer t such that every t tough graph has a Hamiltonian cycle. There exists an integer t such that every t tough graph has a Hamiltonian cycle. So, how big t should be for this to happen? So, this is an interesting question. So, one can this is still open. And now, this is about the relation between toughness and Hamiltonicity. So, while some minimum toughness of oneness cannot guarantee Hamiltonicity, but it is definitely necessary. But if you increase the toughness to some high value, some constant which is reasonably high, it may be possible that that may be enough to guarantee Hamiltonicity. So, is it it's an interesting question to try. And now, we will get into another related result. So, somehow this Hamiltonicity is related to the 4-color conjecture. How is it related to the 4-color conjecture? So, it's I will just briefly explain the sequence of arguments. This is essentially due to Tate, and when Tate tried to prove the 4-color conjecture, he observed first observation you have to make is the 4-color conjecture can be reduced to simple 3 connected maximal planar graphs. See, what does 4-color conjecture say? 4-color conjecture says, we have seen it earlier, that every planar graph can be vertex colored using properly vertex colored using 4 colors, at most 4 colors. So, of course, we can concentrate always we can concentrate on maximal planar graphs, because if every maximal planar graph can be colored using 4 colors, any planar graph also can be 4 colored. Now, what do we mean by maximal planar graphs. To remind you, it means that you keep, if you are given a planar graph, you keep adding edges until you cannot add any more edge without losing the planarity, right. So, we also know that all maximal planar graphs are triangulations. So, it is just easy to see that the problem of asking, the question of asking whether a planar graph can be all planar graphs can be colored using 4 colors is equivalent to asking whether triangulations, that means the triangulated planar graph, the maximal planar graphs can be colored using 4 colors. It is also not very difficult to get rid of the cases where the connectivity is 2 or 1 or okay, disconnected graphs anyway is easy to handle, because we have to only color each component. One connected case also it is not very difficult to show that. So, that if each component is can be colored, then together it can be colored using 4 colors. Similarly, 2 connected case can be handled, that I will leave you to work out. So, the point is, so by some little effort we can show that if you want to prove 4 color conjecture, we just have to concentrate on 3 connected maximal planar graphs, 3 connected planar graphs, and you can always make it maximal, right, by adding more edges, because see the chromatic number can only increase by adding more edges. Therefore, if you show it for the maximal case itself, then that is enough, right. So, so now what we will do is, instead of looking at these 3 connected triangulations which are the maximal planar graphs, we will rather look at its dual. So, that dual is a concept which we did not discuss during the when we studied planarity, but it is a very simple concept. So, so suppose, so we have a drawing, right, something like this. So, we can consider each face as a vertex. Say here I can associate a vertex corresponding to each face. So, we are constructing a different graph. The original graph is this one, the black one, and now I will construct a red graph from the original graph by this rule. Corresponding to each face, we will assign a vertex, and whenever 2 faces are adjacent, that means there is one edge between them, then I will put an edge connecting them like this, right, like this. So, because these are separated by just one border. So, it is not that I can put an edge between this and this will not come, right, because this is too far. So, this way I can construct a planar graph. So, this is also, it is very easy to see that this is also a planar graph. This is the dual of the given planar graph, the black graph's dual is the red graph, right. Now, the point is that, so if you want to vertex color the given planar, the black graph, you can in fact concentrate on the dual and color the faces of it, isn't it? Color the faces of, for instance, if you want to color this vertex, then we could have asked for a face coloring, because so the reason is that if you look at the dual, in the dual, so this will become a face. See, for instance, this is a face of the dual, right, and this vertex of the original correspond to a face of the dual. See, look. So, therefore, if I want to color the vertices of the original, it is equivalent to asking, can I color the faces of the dual in such a way that whenever 2 faces are adjacent, they should get different colors. For instance, this face is adjacent to say this face, this face. So this face and this face should be colored differently from this face. This is what we are saying, right? So it's very much equivalent to the original question, because you see this face correspond to this vertex which is sitting in the middle, and this face, the yellow face, correspond to the vertex which is sitting in the middle. We are essentially saying assigning the color, one color to this one color to this one. Therefore we are just asking that two adjacent vertices of the original should get different colors. So when we are saying that in the dual, the faces which are adjacent should get the different colors. If you remember the original problem, the map coloring problem, which from which we define the 4 color theorem, is very much like this, because these are the countries, right? And then we just decided to assign one vertex for each country. Whenever two countries were sharing a border, then we put an edge between the two countries, right? Two vertices correspond to the country. So we are going back to that map picture, that's all. So that's all you have to see. So therefore we can see that it's a question of face coloring the faces of the dual. Then what can I tell about the dual? What is good about dual? The good thing about the dual is that it's a cubic graph. Why is it a cubic graph? Because in our original graph we have a triangulation. We have a triangulation. Though I drew the other picture, yes, our picture will be something like this. It will be a triangulation. It will be a triangulation because we made it maximal. We just added as many edges as possible. For example, if you don't remember it, if you had a face in the planar graph, in the planar drawing like this, then you can always add one more edge like this, right, until it becomes triangulated. You can add one more edge. So this is now all triangles, right? Because otherwise, once you get to this picture where all are triangles, then you cannot add any more edges, right? So then, because if you want to add any more edge, you will have to cross. So that is the picture, right? So therefore when you considered three connected, if you remember, we considered three connected and three connected triangulation, that means three connected maximal planar graphs in the original. In the dual we will get three connected cubic graphs, three connected cubic graphs. So this is a little bit of cubic graphs, is because it's very easy to see, because if you take any vertex here in the, so you put a vertex for a face, because there are three, it's a triangle, there are three edges going out of it. So that's why every vertex is going to have degree 3 now here, right, like this, degree 3 now, right. Degree 3 now. So it's the dual is going to be a cubic graph. Cubic graph means the degree of each vertex of the dual is going to be 3, and it will be a 3 connected, because the original is 3 connected, and so the question will become like this. Considering the dual, we get that 4 color conjecture is equivalent to the assertion that every 3 connected cubic plane graph is 4 face colorable. So we can color the faces of the dual with 4 colors, is what we want to prove. And the dual, what is the description of the dual? The dual is just a 3 connected cubic plane graph. So if we can show that every 3 connected cubic plane graph, the cubic because of the triangular, 3 connected because the original is 3 connected. So so we just have to prove that 3 connected cubic plane graphs are 4 phase colorable. Now, the next statement is interesting. So, Tate observed that a 3 connected cubic plane graph is 4 phase colorable if and only if it is 3 edge colorable. So, instead of looking at the phase coloring of the planar graph, we can rather look at the edge coloring of it. We wanted what is 3 edge colorable means? It means we can color the edges of, if we can color the edges of that 3 connected cubic planar graph using 3 colors. It should be a proper edge coloring. Proper edge coloring means 2 adjacent edges should get different coloring. Then it can be phase colored with 4 colors. So, every 3 connected cubic planar graph will be 4 phase colorable if and only if it is 3 edge colorable. Thus, what is the conclusion? The 4 edge, then that means the 4 color conjecture will be equivalent to the assertion that every 3 connected cubic graph is 3 edge colorable. Instead of attacking the 4 color conjecture, we can rather try to solve that every 3 connected cubic planar graph, right, is 3 edge colorable, not cubic graph. Cubic planar graph is 3 edge colorable. This is what we will have to show. Now, but how do you establish this thing? Is it easy? So, to show that every 3 connected cubic planar graph is 4 phase colorable if and only if it is 3 edge colorable. So, Tate has this nice argument. Let us quickly go through that. So, what it says is, so we can define the colors, the suppose you got a phase coloring of the given planar graph. So, let us say there are 4 colors. Instead of calling this, usually we call the colors as 0, 1, 2, 3, right. This may be the, or maybe 1, 2, 3, 4, these 4 colors of the, but rather than calling it like that, we will use a different notation. We will call the colors as 0, 0, 0, 1, 1, 0 and 1 1. These are the 4 colors. This can be alpha 0, alpha 1, alpha 2, we can call this, these are the colors. Now, suppose we somehow managed to color the faces of the given 3 connected cubic graph using these 4 colors. Now, his argument is, if you just look at any edge, now this edge is the boundary of, is on the boundary of 2 different faces, one face here, one face here, right, 2 different faces. Now, these 2 faces are adjacent faces, they definitely got different colors. So, you may ask, is it possible that they are the same face? That is not possible, because we are dealing with 3 connected graphs, because if it is a 3 connected graph, it is not possible to have this face and this face be same. So, therefore, the color here and the color here are different, or it is not possible to have 0 0 0 0 or 1 1 1 1 or 0 1 0 1 1 0 1 0 combination, because therefore, we see that the 2 colors will, when you add the 2 colors, the point is to add the 2 colors. So, for instance, if this is 0 0 and this is 0 1, we will add the 2 colors. So, 0 0 plus 0 1 will be added, and then we will write down 0 plus 0 is 0. It is in the modulo arithmetic, we will not go beyond zeros, mod 2 addition we will do, 0 plus 1 is 1. So, we will give it 0 1 color. after adding these two, we will give the color, the corresponding color, whatever results from the addition, that color will be given to this edge, right. This is what, and there are two questions which comes now. Is it possible that we may get more than 3 colors if we do this thing? So, first point to note is that we will get only 3 colors, though there are 4 colors here. When any pair of them if you add, as long as they are different pairs, we will never get 0 0 as an answer, right. So, therefore, we will end up with either this or this, and so therefore, we will get only 3 colors for on the edges. What we are doing is we are looking at the edge, 2 faces are there on two different, and they are different faces, they are not the same faces, and now the face coloring is proper, their colors are different. When you add them up, we will get either 0 1 or 1 0 or 1 1, addition mod 2, and component wise addition. And so, we have colored the edges using just 3 colors. Now, is it a proper coloring? Of course, it is a proper coloring, because if you look at this vertex, so we want to make sure that these 3 colors on this edge, this edge, this edge is different. Now, this face, let us say this is alpha I, this is alpha j, and this is alpha k. What will be the color on this thing? This is alpha I plus alpha k. This edge will get, this is the color which this edge will get, and the color here is alpha j plus alpha k here, right, this color, and here it is alpha I plus alpha j, this is the color. So, now you can easily see that these are all different colors, because is it possible that alpha I plus alpha k is same as alpha I plus alpha j? For that your alpha k and alpha j has to be same, but it is not same, because here this alpha j is given to this face and this face, they are different, because they are bordered, they are adjacent faces, they should get different color. Similarly, if you look at this alpha I plus alpha k and alpha j plus alpha k, if they are same, alpha I has to be the same as alpha j, but alpha I cannot be the same as alpha j, because alpha is the color given to this face, alpha j is given to this face, and they being faces which share a border cannot be the same. So, they are different colors, right. From the vertex point of view, all these 3 edges got different colors. So, it is a proper 3 edge coloring. So, what we have now seen is that if you have a 4 face coloring, we can get a proper 3 edge coloring of the corresponding graph. Now, on the other hand, if you have a proper face coloring, so proper 3 edge coloring, we can also get a 4 face coloring, considering it the reverse thing. So, I quickly explain how it is. What we do is because this is a 3 edge coloring of a cubic graph, proper 3, each color class is a perfect matching, isn't it? Because every vertex has exactly 3 edges incident it, and if it is a proper 3 coloring, then you should get different colors on each of this thing. So, it should be like this, right. So, it corresponds to each color class would correspond to a perfect matching, because everything will get exactly one edge incident from that one color, right, from one color. So, so now what you can do is take 2 of these colors, maybe green and red, right. Using the green and red, you can call maybe this is this green and red if you take, right, then what you can do is you can consider the edges which are green and red alone, they should form cycles, they should form green red, see red green cycles, right, red green. So, as we have seen it several times that when just 2 perfect matchings is put together, they should form cycles, like, because if you follow red then green then red, finally it should have to come back here, right. So it should be a collection of cycles. That means as far as the phase coloring is concerned, if you just considered this thing, there will be the collection of phases. These are definitely two colorable, one color here, one color outside, like that, right, because there is just a collection of cycles. Now for each of the cycles, in inner side you can put one color and outside we will have the other color, right. Now what you can see is, if you had considered say this black and red, there also you will get the same kind of cycle structure, and two colors are possible. Now based, so when I consider red and green, you will get a collection of phases. Each phase is colored with say color 0 or 1, because it is two colorable, right. When I consider the red and green edges, those edges will partition the plane into several phases. Each phase is given either a color 0 or 1. Similarly, when I consider the red and black edges, there also the plane will be partitioned into several phases. Those phases, suppose I again color using 0 and 1, right. Now you can easily see that if you consider the whole graph, then this graph will also partition the plane into several phases, and each phase of this thing can be thought of as obtained by taking the intersection of two different two phases of the earlier two colorings. For instance, when I consider the red and green coloring, we might have got one phase, and then when we considered the black and red edges, we get another partitioning. So you take one phase from that and one phase from that, their intersection will define a phase of this thing. So an example can be seen like this. For instance, if you consider this graph, suppose this is colored 1, 3, 3, 2, 2, and here it is 1, 1, and here it is 2, 2, and 3, 3, and 1. So let us look at this graph. This one, when I say 1, you can say all these ones are reds, and this all these 2s can be greens. 2s can be greens, and the 3s, let it be black. Now if we consider a 1-3 phase, suppose you discard this, so how will you construct this phase, for instance, from, suppose I mark it as this phase. So when I consider 1-3 edges alone, I will see that say this is a phase, this is a phase, red, and you see you concentrate on red and black edges alone, you see that this is a phase, right. I am marking it like this. This is a phase, because I am discarding the two edges, this edges I am discarding. So therefore this is a phase. On the other hand, when I consider the green and red edges, then what will happen? The green and red edges, the one phase will be, so like this, for instance. So now I am say, for instance, when I consider the green and red edges, one phase will be like this, right. It will be like this, and the other face will be inside this. Now, if you see the outer this face intersecting with one of this earlier face is giving this. In other words, what we should do is, when I consider the red and green face, then there are some edges inside the face which are black. So, you imagine that they are all removed, you will see the entire face, and now you put back those black edges. Definitely each of them will be coming from some face of the black red, right, corresponding to the black red, and then so that a particular face will be an intersection of those two faces. Now, you take the color, because either 0 or 1 is the color of both these faces, you pair them up 0 1 or 0 0 depending on where it is coming from, right. So, this will give you a face coloring of the graph. It is very easy to argue that now it is a proper face coloring, because both the faces cannot have for instance, when they are two adjacent things, how can they have two equal colors if they are these faces are separated either by one of these edges, right, which is defining, and then based on that, on two sides if you look, you get two different faces for that particular color. Therefore, it follows that it gives a 4 face coloring. So, now quickly what we have done is we have proved that every 3 connected we have proved that a 4 color conjecture is equivalent to the assertion that every 3 connected cubic graph is 3 edge colorable. It is because if you can 3 edge color the 3 connected cubic graph, the corresponding face coloring is 4 face coloring is obtained, and in the dual it corresponds to the vertex coloring, and then that is enough. That is why. And now, what is the relation between the Hamiltonian cycle? Tate thought that every 3 connected cubic graph is Hamiltonian. That is what he thought. It is not correct. Later Tutt disproved it. But if every 3 connected cubic graph is Hamiltonian, then it is very obvious that it can be 3 edge colored, because the Hamiltonian cycle gives us 2 perfect matchings which are given 2 different colors, and the remaining is a matching, and that will get the 3rd color. Therefore, the assertion will this will be 3 colorable, right. If every 3 connected cubic graph is Hamiltonian, then immediately it will be 3 edge colorable properly, and that will mean 4 color conjecture. But unfortunately, that statement is not correct. Every 3 connected cubic graph is not Hamiltonian. Tutt came up with a counter example. Later, after some time, there were several more examples for this thing, and therefore, that was. But what finally Tutt could prove was that every 4 connected planar graph has a Hamiltonian cycle. So, in the next class we will consider another topic, and one more theorem we may want to I want to mention is that the Fleischner's theorem, that the square of every graph is every 2 graph is 2 connected graph is Hamiltonian, because but I will not touch that. The interested student may read from the little book, Distel's book. Thank you.